Math 11? Chemistry 11 for a sec here. So, you remember this formula? MIVI equals MFVF. The concentration initially, which is the M, times the volume initial equals the concentration final times the volume final. Basically, it means the moles initial equals the moles final. That's where the formula comes from. Because if you take the concentration and you multiply by the volume, you're left with moles. Okay? So if we have 200 mils of 0.6 molar iron chloride, so we have 0.6 molar iron chloride. When that dissociates, how much iron do we have? Iron ions. 0.6, right? It's the same. It's a 1-to-1. How much of chlorine? You have 3 times that, right? Which is 1.8. That make sense? Okay. Barium nitrate. We have 0.8 molar. When it dissociates, the barium is a 1-to-1. The nitrate is 2 times that, which gives me 1.6. Okay. Now we mix these together. This is the like you have one flask of 200 mils of the iron chloride, and you're adding it to a flask of barium nitrate that has 100 mils. These numbers are the concentrations of the ions in each flasks before you mix them. Does that make sense? Okay. Then we mix them together. The concentrations are going to change. Why did the concentrations change? Because the volume is changing. We're mixing 200 plus 100 to increase it to 3. So we're essentially diluting it. Okay? So when you mix them together, the volume changes. I'll say delta volume, which equals a change in concentration. So we have to calculate the new concentration. And that's when you use this M1V1 equals M2V2 formula. So if we're going to do, all right, if we're going to do the iron, concentration final of iron this is just a rearrangement of the equations. The initial molarity, Mi, which is 0.6, times the initial volume. What's the initial volume of the iron solution? 200 mils. Now, when you use this formula, it doesn't matter that if you put things in liters or mils or whatever. It does not matter. As long as the units are the same. They have to be the same. You can't have liters and milliliters. That's going to blow everything up. As long as they're the same, it doesn't have to be liters because the units all cancel. So 200 mils. What's the final volume? 2 plus 1, 300, right? So 300 mils. So we get a new concentration of 0.40 molar. Okay. We can do that for each one. And, well, you don't even have to do it for the chlorine because it's 3 times that, right? So you can literally just go 3 times the concentration of the iron. Does that make sense? Okay, so 3 times 0.4 is going to give me 1.2 molar. I mean, you could go through with the formula. You'll get the same thing. All right, the barium, it's the same thing, except the initial concentration is 0.8. The initial volume is 100. The final volume is 300. And that gives me 0.27 molar. What's the concentration of nitrate? Do I have to use that formula? It should just be double, right? It's going to be double that concentration. So 2 times the concentration of barium. So 2 times 0.27. 0.53. All right. That's the grade 11 question. Okay. So now we're going to take that and jump it and put it into math, or I keep saying math. Chemistry 12. Yes.
How is 0.27 times 2.53?
I don't know.
Because we rounded up,
Yeah.
and then it happened to be rounded down. We rounded up to 2.27.
Yeah, it's just going to be rounding. And now I'm going to do it.
It's 0.26.
Yeah, I rounded that up. So, okay, 0.54. You want that?
No.
I do want that.
We should just carry the decimals because I shouldn't round. I rounded that, right? I should be carrying those decimals. I just didn't. That's all. No. But I should carry them through on this one, is what I'm saying. It doesn't matter. Okay. All right. You want to put 0.54? You can put 0.54. That's fine with me. Just a note, if you remember from chemistry 11, when you add equal volumes, you don't have to do any, well, you do have to do some math, but you don't have to do any of this math. If you add equal volumes, you're cutting the solution in half, the concentration, okay? So if I say you add equal volumes of these, you just divide them all by 2, all right? Okay, so if we add, actually, let's look at this here. Calcium nitrate, sodium sulfate. What is the product that should precipitate according to your data package when you mix these two things together? Yeah. What should be the I can't even say it. Precipitate. It should be the calcium sulfate, right? CaSO4. That's the potential precipitate. Because do alkali metals ever precipitate? Do nitrates ever precipitate? So we can just forget those. You know it's going to be the calcium and the sulfate. Okay? All right. Now, if you mix them, so you've been told up to this point, if you mix those together, you're going to get a precipitate. That's not always the case. So if you mix 0.002 molar calcium nitrate with 0.002 molar sodium sulfate, you do not get a precipitate. But if you mix 0.02 molar with 0.02 molar, you do get a precipitate. Why? What has changed? What's the difference? There's only one difference here. It's the concentration. Right? Right? The concentrations matter. Okay? So, how do you know if why can't I say this word? Precipitate occurs or not? So, it's the KSP. All right, so a precipitation will only occur when the solution or the system is supersaturated. So when you've gone past the saturation point, then you start to get a precipitate. Saturated. Saturated. That's saturated. Bleh. There we go. All right, super saturated. All right, so you've gone past the point, and so then the equilibrium starts to push back, and you get a solid forming, and that was the stuff that fell out of solution in your test tubes yesterday. Okay. All right. So we talked about trial KEQs in the last chapter. Now we're going to look at trial KSPs. This will tell us if we will get a precipitate or not. Okay. So calcium sulfate has a KSP of 7.1 times 10 to the minus 5. That's from your data package, okay, at 25 degrees. if we add equal volumes of 0.002 molar calcium nitrate and sodium sulfate, what's the new concentration if you're adding equal volumes? Just divide it by 2, right? Equal volumes means divide by 2. You cut the concentrations in half. So they're diluted by 1/2, which means calcium concentration, we can write it out here if you want. Calcium nitrate goes to calcium and 2 moles of nitrate, but we don't really care about the nitrate. Initially, it's 0.02. So how much calcium do we have? 0.002. This is before we do the dilution, all right? Because it's a 1-to-1 ratio. Then we mix equal volumes. So what happens to this concentration? Cut it in half. Divide by 2. So we get 0.001 molar. Okay? You don't have to do the M1V1 stuff. The sulfate, same thing. Its concentration is 0.002. If you look at the dissociation, if this is 0.002, what's the concentration of the sulfate before you dissolve it, or before you mix them? Same thing, it's 0.002 as well. Then you mix them together, that increases the volume by 2, i.e. you cut the concentration in half, so it has a concentration of 0.001 molar as well. So now that we know the concentrations, we can calculate our trial KSP, because this is the reaction we're looking at, right? This is the reaction. They both have coefficients of 1, so we're not squaring anything or anything like that. So the KSP is just the concentration of calcium times the concentration of SO4, which is 0.001 times 0.001, which gives me 1.0 times 10 to the minus 6. That's our trial KSP. Then you look at the actual KSP, because the actual KSP will tell you when you have a saturated solution. Is this number bigger or smaller than this number? It's smaller, right? It's 10 to the minus 6. This is 10 to the minus 5. Okay, so our trial KSP is less than the actual KSP. Therefore, are we in a saturated solution? No, we are not. So the solution is not saturated. And if it's not saturated, you have no precipitate forming. Okay, does that make sense? You can still add more to push the equilibrium that way. So the concentrations, they were too low to get over the KSP. Now, if we increase the concentration by a factor of 10, so 0.02 molar, we go through the same process. I know that concentration is going to become 0.01. This is going to be 0.01. So your trial KSP is going to be 0.01 times 0.01, which is 1.0 times 10 to the minus 4. How does that compare to the actual KSP? It's going to be bigger, which means we've gone past the actual KSP. We're in the supersaturated solution, which it doesn't like, so it pushes back and you get a precipitate forming. Okay? So the trial KSP is greater than the actual, therefore the solution is, we can say, supersaturated and shifts left. And it will shift left to precipitate out some calcium sulfate. Okay? Yeah, so you dump it in and it all this is all like this happens like instantaneously, right? But it pushes, I guess for you guys. I don't know my lefts now.
That way.
Left. Sorry. We dump it in, it goes all the way right, ionizes, but then the solution's like, I got too much stuff in the water. The water can't hold it essentially. So then it pushes back, and then because it's solid over here, it falls to the bottom of the container. Does that make sense?
So then why when you put like salt in water, it's pushing back, do you not get like salt?
You do not get what?
So like you put salt in the water,
Yeah.
it like dissolves. But then when it pushes back, why do you not get salt? Is it 'cause it
You
can't-
will if you saturate the solution. If you go past the saturation point, you will have it sitting at the bottom. You have to go past the saturation point though. If you just add it in, you're in this step. You're in this one where your trial KSP is less than the actual KSP.
Just because like isn't because I thought precipitate formed when you had two things that went together that were solid.
Yes, but you have to be past like this. This is technically should form uh, a precipitate, but the concentrations are too low. Right? Hang on.
Can form a precipitate?
I don't want to say can't. I don't want to say please. Okay, 3A. Determine whether a precipitate will occur when the following solutions are mixed. I.e., as soon as that question is asked, that's a trial KSP question. Okay? This is trial KSP. Okay, so 40 mils of 2.5 molar lead nitrate are added to 60 mils of 1.5 molar times 10 to the minus 3 sodium iodide. Okay, first of all, what's your possible precipitate? That's what you got to figure out. So, do nitrates ever precipitate in our world? No. Does sodium ever precipitate? No. So, what is the possible precipitate? Lead iodide. Did I say? Yeah, lead iodide. So, this is your possible precipitate is the lead iodide, PbI2, which when it ionizes is doing this. Okay? Does that make sense? Everybody with me so far? I don't care about the sodium and the nitrate, that's irrelevant. I care about the lead and the iodine. Now, to figure out if we're going to form a precipitate, we need to know the concentrations of lead and iodine. So we look to what we had. We had 2.5 times 10 to the minus 3 molar of lead nitrate, 40 mils of it. These are not equal volumes, so we got to use our M1, V1, blah, blah, blah formula. Okay. So let's go. The concentration of lead final will equal M1, V1 over V2, V final. I use ones and twos instead of initials and finals, but it means the same thing. Okay. What's the initial concentration of the lead ion? Should be that, right? Because there's only one lead ion in this molecule. Does that make sense to everybody? So it's going to be 2.5 times 10 to the minus 3. The initial volume is 40 mils. The final volume is what? 100 because we're adding it to 60 mils. So you punch that in your calculator and you get 0.001. Is that right? Somebody please confirm that. So there's our concentration of lead. Okay. Now we need the concentration of iodine, right? we have to do that. The iodine comes from the NaI. So concentration of iodine will be M1V1 V2. The initial concentration, is this a 1-to-1? Whoa, hang on. Talking about where does the iodine come from? It's coming from this, right? Don't look at this. This is going to be for our KSP. The iodine comes from the NaI. This is important because people mess this up all the time. All right? So there's 1 molecule of iodine for every molecule of sodium iodide. So if we have 1.5 times 10 to the minus 3 molar of this, then that's what we have for iodine as well. Okay? And then the volumes are 60 and 100 again. If you punch that in, 0.0009, 9 times 10 to the 1, 2, 3, 4. 9 times 10 to the minus 4. Is that right? Okay. Now, a lot of you are going to be tempted to multiply this by 2. Do not multiply it by 2. And this is important. Why not?
Because that's the same concentration.
This is the concentration of iodine, and that came from this. It has nothing to do with this reaction right now. This is going to be our KSP reaction. Okay? So, do not multiply by 2. I'm going to say because it came from sodium iodide, which is a 1-to-1 ratio. Okay? That's the iodine source. Now that we have the concentrations, then we look at the KSP reaction, all right, to form the precipitate. So the KSP, or the trial KSP, what's the equation? Don't give me the numbers, just tell me what the equation is for this. So yeah, it's going to be the concentration of lead times the concentration of I minus squared. Does that make sense? It's just a regular KSP question. What's the concentration of lead? 0.001. What's the concentration of I minus? 9 times 10 to the minus 4. That number goes into the equation. Times 2, or squared, I should say. So then if you do that, you get 8.1 times 10 to the minus 10. Okay? So this is our KSP trial. What's the actual KSP of lead iodide? You're going to have to look that up on your table. So we go to our table. Oops. Lead iodide. There it is. 8.5 times 10 to the minus 9. So actual, what am I writing? Oh my gosh. KSP is actually 8.5 times 10 to the minus 9. All right, is our trial bigger or smaller than our KSP? Smaller. Since KSP trial is less than the actual KSP. KSP, no precipitate forms. Okay? So because our trial KSP is less than the actual KSP, no precipitate forms. All right? Okay, these are going to start to get a little funky. So you just got to keep things straight, because later on what we're going to do is we're going to have a common ion effect. We're going to have a solution that already has some iodine in it. Okay? So it's important that we understand these things before we get there. I just want you to do question 3B for sure, and 4. 3B and 4, please. And then that'll be the end of the class. We will have some sort of short group quiz, yes, tomorrow. But it won't be... I gave you like 24 hours.
Yeah, that's a lot of noodles. Wait, it's less than
23 hours. Since February. The whole course. No, it's just this unit. It's just this unit. It will not be. It will not be like the first group quiz. Okay, will not be to that level. I haven't even made it yet. I'm gonna make it in the next block. So.
Wait, can I sit next
Yeah.
to you next block?
What?
Can I sit next to you next block?
No, you smell.